So Flavio, thank you very much for the introduction, and thank you, of course, for the invitation, and thank you everyone as well for joining today this meeting. I hope that, well, you will find our recent research interesting, and I also hope that we can have some good discussions about potential collaborations, and of course, over the course of the presentation, if you want to ask any questions, feel free to stop me, because it's probably more interesting and more fruitful if we are having discussions over the course of the presentation. The title of this presentation is Understanding the Potential of Real Processing in Memory for Modern Workloads. As you will see, most of the slides are coming from two recent talks, two papers that I presented at ESPAS 2023. It's not all the research that we have recently done in real processing in memory for modern workloads. It's mostly like two representative recent works, but we have a few more works that I will mention at the end. And if you want to go deeper into any of them, I will be glad to provide more details. We are going to start with a very brief motivation. I think this is actually well known by everyone. The fact that data movement dominates performance and energy consumption in current computing systems. And just to give you some numbers, some motivational numbers, for example, it has been measured that 62% of the total system energy in consumer applications, 40% in scientific applications, and 35% in mobile applications is spent on data movement. And this happens because in any compute system, for example, this system on a chip, where we have different processors, different accelerators, and levels of the cache hierarchy, there are interconnects between all these components, and also to connect the system on a chip with the DRAM. And there is a lot of data movement over all these interconnects. Because this data movement is consuming so many execution cycles and so much energy, it makes sense to try to find solutions. And one potential solution is to make compute systems more data-centric. And what that means is providing the system with compute capabilities near or inside the memory, basically in order to compute wherever it makes sense. And it makes sense where the data resides at any given time. Processing in memory, as you all probably know, is a trend that has been proposed many decades ago. The oldest paper that we are aware of is from 1969. And since then, there have been like several waves of research in academia, at least, proposing different ways of doing processing in memory, but it was always very challenging, basically due to manufacturing constraints. Up until now, in 2019, UPMEM presented their real-world processing in memory architecture, or processing in DRAM engine, which is based on standard DDR4 DIMMs. And inside, on each DIMM, there are multiple chips, and inside each of the chips, there are small processors called DRAM Processing Units, or DPUs, near each of the memory arrays. And even though this UPMEM PIM system was the first one to be commercially available and publicly available, it's not the only one that has recently appeared. We are aware of several prototypes from Samsung, SK Hynix, or Alibaba, for example. This lecture, of course, the fact that there are already real world processing in memory systems is a great advance. That is very positive towards enabling the adoption of processing in memory in compute systems. But as you probably know, there are still many other barriers that need to be fixed or need to be solved in order to enable this adoption of processing in memory. Today, I'm going to focus on applications and software for processing in memory, because it's something that we have been doing a lot of research in our group in recent times, and we keep doing for sure with many of our students. The two works that I'm going to present today, I think that they are pretty representative of recent research and also good examples of how these processing in memory systems, or at least this one from UPMEM, needs to be programmed and how code needs to be optimized for this system. The processing in memory, in order to define it, is a compute paradigm that advocates for memory-centric computing systems where processing elements are placed near or inside the memory arrays. And as I said, processing in memory is becoming a reality with the UPMEM PIM architecture and the prototypes from the other major vendors. And one thing that we observe is that all these systems have some common characteristics. The first one is that there is a host processor, either a CPU or a DPU, with access to a standard main memory and PIM-enabled memory, so still both coexist in the memory-centric computing system. The second characteristic is that the PIM-enabled memory contains multiple PIM processing elements with high bandwidth and low latency memory access. And these processing elements run only at a few hundred megahertz and have a small number of registers and small cache or scratch pad if they have it. And also it's very typical that these processing elements cannot communicate directly, at least if they are in different chips. So they need to communicate via the host processor. It's something that may entail a significant overhead for some workloads. For others, as we will see today, it may not be, it will be a, let's say, tolerable overhead. And this is how this system looks like. As you can see, there is a host processor, the host CPU, that can access the standard main memory and the PIM-enabled memory. And if we take a closer look at the PIM-enabled memory, we find memory arrays in the form of banks or entire ranks. And we have the PIM processing elements as well, with they might be more or less general purpose. They have different execution models like fine-grained multi-threaded or SIMD. That depends on the specific system, but more or less it's what we call processing near the memory, because the processing elements are close to some memory array. In our work and in this presentation, we are going to focus on the UPMEM PIM architecture that uses general purpose processing cores called DRAM Processing Units, or DPUs. These DPUs are fine-grained multi-threaded. They can run up to 24 hardware threads that are called tasklets in this architecture. And they support 32-bit integer arithmetic, but multiplication and division are emulated, as well as floating point operations. Each DPU has access to its own DRAM bank that is called MRAM and its own scratch pad that is called WRAM. And this is how the system looks, where you can see the dual socket CPU and then some DRAM DIMMs, or some DIMMs of conventional DRAM, and some DIMMs of PIM-enabled memory. So this is the kind of system that we have used in the two studies that I'm going to present next. If there is anything that you want to clarify about the architecture, please let me know. If not, I think we can go ahead and start with the first one of the first part of the presentation. So the work that is, as I said, one of the two that I presented recently at the ISPAS 2023 is titled Evaluating Machine Learning Workloads on Memory-Centric Computing Systems. And I'm going to start with an executive summary. Machine learning training is computationally expensive and typically memory bound because it needs to access large training data sets and access them repeatedly. And one way to optimize the execution of these machine learning training on real compute systems is to use processing in memory to alleviate the potential data movement bottleneck. We have done so using the UPMEM PIM architecture with the goal of understanding the potential of modern general purpose PIM architectures to accelerate machine learning training. And as you will see, we have implemented 4 classic machine learning algorithms that are linear regression, logistic regression, decision tree, and k-means clustering. And we have characterized these implementations in terms of quality, performance, and scaling, and compared to their counterpart CPU and GPU implementations. Just to give you a little bit of summary of the results, we have seen especially good improvements for decision tree and for k-means, basically because they use operations that are natively supported by the UPMEM PIM architecture. We will go into details later. Our work is publicly available, and the source code is in the repository, as you can see. And we have done an experimental evaluation on a real-world processing in memory system with more than 2,500 PIM cores. And as you will see, well, this presentation and the paper is full of key observations, takeaways, recommendations for ML workloads on general purpose PIM systems. We are going to start very briefly talking about the machine learning workloads that we are targeting in this work. About processing in memory, I guess I don't need to say much more, because I already introduced or mentioned the type of system that we are targeting here. I will briefly talk about the implementation of the ML workloads, and finally we will go to the evaluation. So as I said earlier, machine learning training needs to access large amounts of data and requires many iterations, and this causes frequent data movement between memory and the processing elements, and the amount of computation might not be enough in all cases to amortize the cost of moving the training data to the processing elements due to low arithmetic intensity or low temporal locality or irregular memory accesses. So our goal is to study and analyze how real-world general-purpose PIM systems can accelerate machine learning training, and this is why we chose 4 representative ML algorithms: linear regression, logistic regression, decision tree, and k-means that are memory bound. And we observed that when using the roofline model to characterize them, we observed that all 4 workloads fall in the memory bound area of the roofline. So they are potentially good candidates for processing in memory. I can skip these slides because they basically repeat the same ones I showed earlier. And again, the PIM system that we have used for the implementation and for our analysis and characterization. So let's discuss how we implemented these 4 workloads on the UPMEM-based PIM system. The workloads, by the way, show some diversity in terms of memory access patterns, operations and data types, and communication and synchronization. As you can see, for example, in terms of the computation pattern, the first 2 workloads use multiplication more intensively than the other ones, and also might need to use floating point computation, and that's why they are they will be pretty much bottlenecked in this architecture, but still we can apply certain optimizations to improve the performance, as we will see. I don't want to spend much time on describing the specific implementation. I think that probably you all are familiar with these algorithms. Linear regression is a supervised learning algorithm where the predicted output variable has a linear relation with the input variable. We have used gradient descent as the optimization algorithm, and we basically in the PIM implementation try to distribute the workload equally over the existing PIM cores or DPUs and the tasklets or PIM threads. And whenever it's needed, we move partial results to the host for final reduction or result merging, and eventually redistributing the workload over the PIM cores in the multiple iterations. And that's more or less what we are doing for the 4 algorithms. So as I said, I don't want to spend too much time on explaining the specific details of the implementation. I think it's interesting to mention here the different versions that we implemented for the different algorithms. In particular, we did that mostly for linear and logistic regression because there is more room for optimization and improvement on this architecture. So That's why we have 4 versions of linear regression. The first one uses 32-bit real values, or 32-bit floating point values. The second one uses fixed point representation in the 32-bit integers. After that, we develop a hybrid version that starts using 8-bit values and increases the precision as needed up to 32 bits. And finally, the last one is a version that uses custom multiplication that we implemented ourselves using built-in functions. For logistic regression, we follow very similar way of distributing the workload. The key difference with respect to linear regression is that it uses sigmoid, the sigmoid function, and sigmoid, because it requires exponentiation, is pretty challenging to implement in this architecture that has even though it's a general purpose, it has a relatively small instruction set or reduced instruction set. We have 6 versions of the logistic regression. The first one uses floating point numbers and approximates the sigmoid computation with Taylor series. The second one uses 32-bit integers. And in the third one, we replace the calculation of sigmoid with Taylor series with a lookup table. And this lookup table might be in MRAM, which is the DRAM bank, or might be in WRAM, which is the scratchpad. And then same as in the linear regression, we also have a hybrid version, and we have a version that uses the custom multiplication. For decision tree, there are several commands that the PIM cores can execute depending on these commands that the host sends to the PIM cores, different tasks. And these tasks are split commit, split evaluate, and min max. So there is somehow task level parallelism because different cores might be doing different tasks at the same time. One thing that we paid special attention for this decision tree is the data layout. We mapped the tree with the features and the different leaves in a way that it guarantees that we are going to have streaming memory accesses to the DRAM bank. And we need to do that because that's the way of maximizing the bandwidth. And basically, that's the biggest strength that this PIM system has. So we should try to avoid fine-grained memory accesses. It's much better to access in streaming. And the last one of the 4 workloads is k-means clustering. In this case, again, we distribute the data set evenly over the PIM cores, and then the PIM threads start checking in for each of the inputs, what's the closest centroid, and they need to update some counter and accumulator that are later used by the host to recalculate the centroids. So let's take a look at the evaluation, which I think is where we can have more interesting observations and takeaways of this work. We used different data sets, synthetic data sets, especially for the strong scaling and weak scaling analysis that we did, and also real data sets for the comparison to CPU and GPU. And here we have evaluated an UPMEM PIM system with 2524 PIM cores, an Intel Xeon CPU, and an NVIDIA A100 GPU, and we compare or we evaluate quality metrics, performance of PIM kernels, performance scaling, and comparison to CPU and GPU. And this is again the picture of the system that we have used in our evaluation. In terms of the quality metrics, we observed that overall the accuracy of the quality of the results it's very similar to that of the baselines, the CPU and the GPU. Only in the case of linear regression and logistic regression, where we are quantizing and using hybrid precision, we see a reduction in the or an increase in the training error rate, but it's still it remains low and close to that of the floating point version. It was interesting to observe that the LUT-based versions obtain lower training error rates than the versions that use approximation, basically because they are using exact values in the lookup table. And for decision tree and for k-means clustering, basically very similar accuracy to the CPU baseline. So now let's take a look at the analysis of the PIM kernels, because one thing we did here was studying the performance or measuring the execution time of the individual kernels for the different workloads, and this way we could evaluate as well what was the improvement obtained with the different optimizations that we applied. One general observation, not only for this linear regression, but basically for all kernels, as we will see, is that all versions saturate at 11 or more PIM threads, and that's something that we already knew that, or we were already expecting that was going to happen based on our prior work, where we evaluated the arithmetic throughput, we measured the arithmetic throughput, we observed that the arithmetic throughput saturates at 11 or more tasklets or PIM threads, and the reason for that is the number of pipeline stages of the DPU, of the PIM cores in the UPMEM system. We see significant performance improvement when moving from floating point to the fixed point representation, basically an order of magnitude performance improvement. That makes sense as well, because floating point operations are not natively supported, and maybe even a single addition or a multiplication might take hundreds of cycles on this pipeline. So one first key takeaway is that workloads with arithmetic operations or data types that are not natively supported by the PIM cores run at low performance due to instruction emulation. So whenever it's possible, we should use fixed point representation if it doesn't cause much accuracy loss, in case that the PIM cores do not support floating point computation. For other PIM architectures, this recommendation might not be applicable because they may support floating point computation, but still they will support some specific data type. For example, the proposals from Samsung or from SK Hynix for machine learning and artificial intelligence support 16-bit floating point, which might be better in some cases, but not in all cases for sure. So in the end, these PIM architectures have pretty restricted instruction sets, and we should try to use those operations that are natively supported. For linear regression as well, we observe a performance improvement 41% faster than the 32-bit integer version. This 41% is for the hybrid version that uses quantization and hybrid precision. Basically, because instead of using 32-bit multiplications all the time, because remember that even 32-bit multiplication, integer 32-bit multiplication is emulated, if we replace that with 16-bit or 8-bit multiplications, we can see significant performance improvement and even further improvement for the version that uses the custom multiplication. So these are two recommendations as well from our work, using quantization, hybrid precision, and also, whenever it's possible, to optimize code leveraging native instructions, as we did, for example, with the 8-bit integer multiplication. And the results for logistic regression. So first of all, is that for both the 32-bit floating point and the 32-bit integer versions, we see very high kernel time, and that's due to the sigmoid approximation. When we move to using lookup tables in MRAM or in WRAM, we see more than 50 times performance improvement. So the recommendation is to use memoization or lookup tables, storing pre-calculated operation results in memory, and I mean that can be basically a good practice in processing in memory systems, because even though lookup tables might not be the best solution for conventional processor-centric systems like CPUs or GPUs, in the case of PIM systems, we have a much larger amount of memory and much higher bandwidth and lower latency access, and it might make a lot of sense to use lookup tables for at least those operations that are not natively supported. And we also observed additional improvements from the hybrid version and the version that uses the built-in multiplication. So overall, if we look at all the different kernels, as I mentioned earlier, all of them saturate at 11 or more PIM threads. And in the UPMEM PIM architecture, this means that the pipeline latency hides the memory latency. The UPMEM PIM architecture can provide very high memory bandwidth for the DPUs, for the PIM cores, and if we manage to have access to it in streaming, it's likely that most of the times the execution of arithmetic operations on the pipeline hides the latency of the memory accesses of moving the data between the DRAM bank and the scratchpad. This is a general observation. We have seen this mostly in all the different kernels that we have implemented, not only in this work, but also in previous works as well. And that's because let's say, fundamental takeaway here is that most real kernels behave as compute bound on the UPMEM PIM architecture. So key takeaway number 2, with respect to the ML workloads, is that they are memory bound due to the low arithmetic intensity in CPUs and GPU, but they become compute bound when running on PIM. And the recommendation is to maximize the utilization of PIM cores by keeping their pipeline fully busy. And this is I think it's a key difference with respect to conventional processor-centric systems, where you may not have the best performance when using the compute units as much as possible. For example, if you think about GPUs, where we have this concept of the occupancy of the GPU cores or streaming multiprocessors in NVIDIA GPUs, higher occupancy doesn't always mean higher performance. However, in PIM systems, we can expect that if we keep the pipeline or the execution units more occupied, more busy, the performance will be better. Okay, so now the next thing is performance scaling. We run strong and weak scaling experiments. Here I only have results for strong scaling experiments. And the first observation is that the PIM kernel time scales linearly with the number of PIM cores. So notice that, here we have evaluated all the different versions of linear regression. This is logistic regression, and these are decision tree and k-means. And the number of PIM cores goes from 256 to 2048. We see that the execution time decreases linearly with the number of PIM cores. And also an interesting observation as well is that there is very little overhead from the communication between PIM cores. What we call here inter-PIM core communication is the movement of data from the PIM cores to the host back and forth between iterations of the training process. And there is very little overhead from that, and also very little overhead from the communication between host and PIM cores at the beginning and at the end of the training process. I think that this is really good news in this specific system, because we know that one potential bottleneck in these PIM systems is that the PIM cores cannot communicate directly, but that doesn't seem to be a big issue for these 4 workloads. So a key takeaway number 3 is that ML training workloads which need large training data sets benefit from large PIM-enabled memory with many PIM cores. And even if they need to communicate via the host processor, the amount of data movement needed for intermediate results is tolerable. Okay, so now let's take a look at the comparison to CPU and GPU. We have here some results, execution time results with a logarithmic scale for linear regression and logistic regression. And the first thing that we can observe is that those versions that use operations that are not natively supported by the hardware, as is the case of the 32-bit floating point versions, they are heavily burdened and very far from the performance of the CPU and especially the GPU. However, at least good news here is that the different optimizations that we applied, quantization, hybrid precision, the custom multiplication, really were able to close the gap with GPU performance. And even though they are still lower than the GPU, but at least improved performance a lot with respect to the initial 32-bit floating point version, and also outperform the CPU versions. For decision tree and for k-means, the results are better, basically because these ones don't need to use expensive operations such as multiplication or floating point operations. And this is why we see for decision tree 27 times the speed up over the CPU and 1.34 times speed up over the GPU version. For decision tree is respectively 2.8 and 3.2 times faster than the CPU and the GPU. We have additional implementation details, more evaluation, and extended observations, takeaways, and recommendations in the long version of this paper in arXiv, where you can also find these results for the Creo dataset that is even larger than the one that I showed in the previous slide. And we see, in fact, increased speed ups for at least decision tree, up to 62 times faster than the CPU and 4.5 times faster than the GPU version. The main reason for this is that now the dataset is larger for decision tree, and this makes that the best performing number of PIM cores is higher as well. Now we are using all PIM cores in the version that, or in the configuration that obtains the best performance. This is not the case for k-means. For k-means, we see more or less very similar speedups as in the other dataset, but that's because for the other dataset, we were already using the maximum number of PIM cores for the best performance. So one key takeaway is that ML workloads that require mainly operations natively supported by the PIM architecture, and that's the case of decision tree and k-means, can outperform their CPU and GPU counterparts. And I think that this is especially interesting if we compare to the GPU that we use. It's an NVIDIA A100 GPU. It has an memory bandwidth, global memory bandwidth of 1.5 terabytes per second, which is not much smaller than the total bandwidth of the PIM system, which is about 2 terabytes per second. However, the fact that the PIM DIMMs are also connected to the host processor via the memory channel or the memory buses also provides more bandwidth between the main memory of the CPU and the PIM-enabled memory than the bandwidth that we can typically obtain over PCI Express bus. So that's also one of the reasons why for these two kernels or these two algorithms, the PIM versions outperform the CPU and GPU, or the GPU specifically. As I said, you can find more details in the long archive version, and the code is also publicly available in our repository. So yeah, well, this is just the executive summary again. With our main contributions, the PIM implementation of these 4 classic machine learning algorithms, characterization and comparison to CPU and GPU. If you guys have any questions now about this work, we can discuss now.
Yeah, I have a little question. Yeah,
okay, go ahead.
Here we see a thanks. Here we see a comparison between the performance of GPU and the PIM architecture on the same problem. But my question is, in your opinion, what you see in the future of the PIM? This relation between GPU and PIM could be in the future become how to say, works together to get result. So using there exists some type of algorithm in which PIM and GPU can work together instead of be a competitor, as we see here.
Yeah, I definitely agree with that point of view. I think that processing in memory is not, or should, the general concept of processing in memory shouldn't be seen as a standalone accelerator, but rather as a complement to CPUs or GPUs. In this case, or in these studies that we are doing now, we are comparing with GPUs because the PIM system, specifically the PIM system that we are using, can be seen as an external accelerator or as a coprocessor, and in that sense could be seen as a direct competitor of GPUs. However, I think that processing in memory is something even wider and can be, as I said, a good complement for CPUs, GPUs, or maybe even FPGAs or other types of processors. So I expect that in the near future we will see also systems where processing in memory accompanies GPUs as well. So we have processing in memory units in the global memory of the GPUs.
Okay, thanks.
Yeah, that's yeah.
Paolo, if you are,
yeah. So that was a very inspiring talk. So thanks for that. So I have a dozen of questions, but we will restrict to a couple. The first one is, how much effort do you think that the compiler designer needs to put in democratizing, let's say, the use of processing in memory, and how much will the programmer need to work on to take advantage of the architecture?
Mm-hmm. Yeah, that's a very good question, I think, and I think that there is a lot of work to do in this direction. So first of all, programming the UPMEM PIM system is not really very complex, not very complicated. These days, most of us are familiar with CUDA programming. GPU programming, for example, is something that is being studied in all universities in parallel programming courses, and I think that we have made a very good progress in the last decade at least in programming parallel systems. And in that sense, I think that programming this PIM system is not difficult. It's not going to be more difficult than programming a GPU. It's probably easier. But the question, but in the end, the main question is about the big challenge here is starting to port new applications to a new system, right? And that that's something that happened to GPUs 10 or 15 years ago, and now will happen to PIM systems as well. However, I think that in that sense we have also made a lot of progress in the last few years or in the last decade in terms of high-level programming languages that can generate high-performance code for different platforms. I think that new frameworks like MLIR can facilitate this a lot, especially for many of the applications that seems to be, or many of the kernels that seem to be really good candidates for processing in memory, like linear algebra, for example. That's relatively easy to generate code for a system like UPMEM or other systems like Samsung or SK Hynix. Of course, there is a lot of work to do, but I think that it's something doable. It's probably if these architectures themselves show promise, show interesting performance improvements for important workloads, I think that adapting the high-level programming frameworks and compilers to these new architectures won't be the biggest barrier. But
okay, so
yeah.
Second question, which is more related to my expertise in reliability. So definitely memory is traditionally the most vulnerable part of the system because of the area. And DDR are nowadays extremely weak. So you can have a lot of permanent intermittent transient errors in memory. And normally ECC helps a lot in reducing that. In this architecture, do you also consider ECC in memory, and how does the two integrate? So is the processing in memory comes after the ECC? Does it seize the memory cell, the raw memory cell, or the logic value that comes after the ECC? Do you have any expertise in that?
Mm-hmm. I cannot remember right now. I cannot remember right now if this UPMEM system has support for ECC. It probably has. In terms of, I can't remember for sure the Alibaba prototype for recommendation systems. They do have on-chip ECC. In each memory bank, they are reserving some space for ECC, and I assume that there is some on-chip ECC that takes care of it. So I think that this is something that in general can be supported for PIM systems. Or I don't know, other reliability issues that affect processing in that affect DRAM might also affect here as well. But I also believe that the vendors are pretty conscious about that. Like, for example, I know that UPMEM filed a couple of patents about the row hammer problem in DRAM, and supposedly their DIMMs are protected against row hammer. I don't know the specific details of these patents either, but yeah, I mean, it is at least something that is in mind for the vendors. I think that reliability is going to be or will be more of an issue for other processing in memory proposals that we in our group call processing using memory or processing using DRAM, where the computation is directly done with DRAM cells. For example, activating, you might be familiar with these works, like activating 3 DRAM rows in the same subarray at the same time. We obtain a majority function, and that can be useful to implement more complex operations. So for these kind of proposals, I think that reliability is a bigger issue. First of all, because we may not only obtain the results that we expect, and second, because providing ECC support is going to be more challenging, if even possible.
Okay, perfect. Thanks a lot.
Yeah.
Marzio?
Thank you for the question.
Yes, I have a very quick question, and that would be from what I've understood in the presentation, currently PIMs are very useful for large computation, accelerating large machine learning models. So, like going towards scientific computing, high performance computing, this sort of tasks. But you also acknowledged at the start of the presentation that there's a very high let's say saving in terms of power by reducing the number of data movements. And my question would be, what do you foresee an advantage in using this kind of technology also in consumer grade electronics? So I'm thinking like mobile embedded systems, or even like laptops, or just consumer grade processors, because we've seen these evolutions with GPUs already and AI accelerators, and I'm thinking like, is it justifiable to use this kind of architecture just for the memory saving alone, or it could also be useful for, let's say, workloads of the future, which we cannot foresee right now for laptops or smartphones or whatever?
Yeah, I think that's a very good question and a very good point. I think that there is a lot of promise for processing in memory or near data processing in general for mobile systems, and it's something that it can be really necessary to reduce the energy consumption in these kind of systems. And there are some recent works that have shown that from our group and from other groups. Like, for example, in the beginning, you remember that I mentioned energy consumption in consumer applications. That's a work that our group published in 2018 for an analysis of different Google workloads on on mobile devices, specifically on Google Chrome. And more recently, there was another work focusing on edge DPU. And there are a few other important papers from other groups as well. So I think that there is a lot of promise and need as well for something that alleviates the energy consumption. The only thing is that these existing systems from UPMEM or also the prototypes from Samsung or from SK Hynix seemed right now more focused on other types of systems, like server-grade systems, I would say. But I guess it's because of either the memory technology that they are using or the applications that they are targeting. But yeah, I think that in mobile systems, PIM makes a lot of sense for sure as well. Or processing near the storage as well, which is another important trend, and can save even more energy, right? Because we normally need to move large amounts of data from the SSD to the memory before processing it. There will be, or there are for sure, many workloads where we can start alleviating this data movement earlier.
Okay, thank you, Marcio. Sinan?
Yes, maybe a comment and also a short question, which is related to the one Paolo asked. You probably know, right, that to PIM or not to PIM work, which has been published in ISCA 2012. So, I mean, the main takeaway of that paper is like everything is very application specific, and you need to know, right, the characteristics of the load, like how parallelizable it is, how vectorizable it is, what is the I mean, what does the underlying architecture, PIM architecture provides to you? So you should have a really extensive, maybe detailed compiler analysis to understand if it is logical or beneficial to load that thing in PIM on PIM or not. So it looks like the compilation or compiler analysis, static analysis, maybe is very, very important to understand or to exploit the benefits of PIM, I guess. This is something that I wanted to just mention and get your opinions indeed.
Yeah, you mean to PIM or not in ISCA 2021?
Yeah, yes, 2021. I don't remember exactly, but
yes, I remember that work. It's an interesting work because it's a kind of a similar platform to this UPMEM PIM system, even though it's not the same, because there they are considering RISC-V processors, and these are not RISC-V. I think, if I remember as well correctly, that work used simulation, not a real system. I'm not aware of any real PIM system with those characteristics. And definitely, I agree with you that finding parallelism and vectorization opportunities is necessary for the I mean, it's definitely necessary before porting anything to a PIM system. In the case of the UPMEM PIM architecture, there are no SIMD units, so we don't have to worry about vectorization that much. It's only parallelism, but still, most of the workloads that you can parallelize in this UPMEM system can also be vectorized because there is you will typically exploit data level parallelism. I agree on that. I think that will exist for sure. I think that most important workloads these days have a lot of parallelism, even if it's irregular parallelism, as we can find in sparse linear algebra or graph processing. There is a lot of parallelism, even if it's irregular. The point is to find the right execution units for each specific workload, but there will be parallelism in most of the workloads. And from that to PIM or not work, I think that it's one especially relevant contribution is the fact that they came up with a performance model. And based on that performance model, they can also figure out when something is good for offloading to PIM or not. And I 100% agree that that's important, and it's something that we should try to have in all different PIN systems as well. In the case of the UPMEM PIN system, it would be for sure possible to have that sort of performance model as well, because one thing that we have observed in our prior work is that the execution is quite deterministic. If you know what's the computation that each pin thread or tasklet is going to do in the inner loop, let's say, you can easily count the number of instructions there, estimate what's going to be the latency of those instructions in the pipeline, and then depending as well on how large or small are the accesses to the DRAM bank, we can also estimate the latency of those memory accesses. And I think it's possible to create this sort of model, and it's very useful, very important if it can be used at compile time to make scheduling decisions.
Thank you very much.
So we have other.
Yeah, thank you for the question. Yes.
Kahim.
Yeah, yes, thanks for the presentation, Juan. I have a question related to the architecture itself. I mean, instead of adjusting workload and mapping it properly to the existing architecture, near memory architecture, do you have any recommendations based on your experience and observations how to improve the architecture of processing in memory or near memory processing architecture itself, to adjust maybe it to the modern workloads?
Yeah, that's definitely a very good question, and it's what we also try to do, that come up with this sort of recommendation in all our works. We do this analysis for different workloads. I think it of course depends on the workloads that you want to target. I think that we will see general purpose PIM systems, but they might not be as general purpose as CPUs and GPUs, because in the end you have much less area for every single core. So it's going to be very difficult to have a lot of support for many different operations. But there are for sure a few things that I would suggest as potential improvements for these UPMEM PIM architecture, and potentially for others as well, as you know, in the type of system that I mentioned in the beginning of the presentation. I think that it should be clear that not having native support for 32-bit multiplication is an issue, because in the end, I mean, I'm fine with not having support for floating point computations, because even if you need to use real numbers, you can use fixed precision, fixed point representation. But 32-bit multiplication seems to be important to many workloads. So that could be one thing. I can understand that in the case of UPMEM, where the area is, I mean, they might not want to occupy too much area of the DRAM chip with the processor in order to still have a decent size for the DRAM banks. I can understand that they decided to be economic in that sense, in the sense of the 32-bit multiplier, but I think that that would be an important improvement. Another thing that I could definitely try to enable is internal communication, at least inside the same chip, because there have been several proposals for years. I know the row clone work from our group presented in Micro 2013. They already proposed a couple of ways of moving data inside the same DRAM subarray, or between DRAM banks, or inside the same DRAM bank. So, and I don't think, I mean, of course, there will be challenges to enable that sort of internal communication, but it's for sure not impossible. So that would be something that I could enable for sure, because it may reduce the, I mean, if you have, let's say, 8 processors inside the same chip and they can communicate directly, you might reduce the amount of data movement for inter-pin core communication that now always happens via the host processor. You can reduce it by 8, no? So potentially, no? So that could be something that would enable for sure. And then the last point that I would suggest, and I think that there is interesting research to do in that direction, is really making this PIM memory as main memory. Be able to completely replace a standard main memory with this PIM-enabled memory, because that will save the data movement that you for sure need to have at the very beginning and at the very end of the execution, which, as we see in our analysis, might not be so terrible for many workloads, but is bad for other workloads for sure, especially if you want to do relatively fine grain of loading. Like, for example, imagine that you have a large array and you say, oh, this parallel reduction can be done very fast in the pin system. But if you need to move the entire array to the pin system and then do the reduction there, probably the data movement, the initial data movement for the input array will be pretty considerable. So yeah, I think that those are 3 things that I would for sure optimize, but there might be more.
Yeah, thank you very much.
Next and probably last question, because then we have to have an internal discussion with Juan. I actually have a lot of questions, but I will ask him afterwards. So Muat, is your last question?
Is the locality of data in the workload makes the difference between the GPU and PIM, or is it does it behave similar to the GPU?
Yeah, that's a good question. I think that this is quite different to GPUs. In a GPU, you have multiple cores, and each of the cores have, I mean, all cores have access to the same memory space, right? To the same global memory and the same L2 cache. So you don't really have to worry that much about how data is placed. Let's say, with respect to, for different cores. I mean, in GPUs, for sure, you need to worry about placing data nicely to have coalesced memory accesses, but that's, let's say, more local thing, right? At the warp granularity. However, here you really need to worry about partitioning the data in a way that you maximize the local accesses, because if you have to go somewhere outside the local memory, you'll have to finish the kernel and then do some data movement and then continue the execution. So in that sense, I think it's even more critical than in GPUs.
Okay, so probably I will ask something to just conclude this public part of the talk. And my question is related to the architecture. First, if you can comment about the fetching the code execution cycle for the PIM part. Second is about communication and synchronization exactly. And the third question is about cooperation. So we see a lot of parallelism so far, and especially parallelism when you have streamed data. So probably one challenge is now writing for this kind of PIM, writing better lock-free algorithms.
Yeah, that's actually a good point. So the first part of the question, you mentioned execution cycles.
What about actually the fetch and decode execution cycle is managed at the PIM level, if they have a branch divergency, these kind of things? So if who manage actually the fetching the instruction there. So if you have synchronization, if you need to follow a different program path, what's going on that specific part when you are just above the PIM. So if the course needs to be synchronized in a like SIMD version, or if they work as a MMD actually architecture. This was the first.
Yeah. So the PIM threads, the tasklets are scalar threads, and that means that there is no execution in lockstep or something like that, so you don't need to worry about divergence. So each PIM thread can execute completely different codes, completely different tasks. The scheduling of instructions is done I believe is in a round robin fashion. In every single cycle, one new instruction from a different thread is fetched and issued onto the pipeline. And the advantage that this has is that you don't have to worry about data dependencies in the same thread. So basically, there is no need for stalls or for data forwarding in the pipeline because you have a different thread every cycle, and you cannot schedule one instruction from the same thread if it's not 11 cycles apart. So also you cannot exploit instruction level parallelism inside the same thread, but you exploit thread level parallelism. Yeah. So I think you also asked about the access to DRAM, right? To the DRAM bank.
The cooperation. Yeah. For example, yes. I think they don't have atomics.
They don't have atomics, but they have synchronization mechanisms. There are mutexes, there are handshakes, barriers, and semaphores. They are not especially efficient, but if you use them with caution, let's say, you use them where they are really necessary, the overhead is quite tolerable in most cases. So the way that the mutex works, for example, is by using some atomic bits that are set by one individual tasklet, and the other tasklets will have to wait before accessing the critical section until the specific lock is free. So yeah, I mean, these might be costly if you use it very frequently, but if it's just like, I don't know, like for example, updating a global variable because you want to fetch the next element to process from a queue, that's something tolerable. Or if you have a parallel reduction and eventually use a barrier or something like that, can also be it's also fine. It shouldn't be too much overhead. But yeah, I mean, at least in terms of programmability, these features exist and they can be used. And I think that in the future they will also be optimized. The hardware can be improved to support them better.
But also other vendors share the same design compared to UPMEM, or this is just specific to UPMEM? So what do you see from, for example, for Samsung? So they have more or less the same design, or they are?
No, it's completely different design. I mean, there are similarities for sure in from the, let's say, big picture of the entire system. There are similarities, but if you go to the specific details of the cores or the execution units, they are completely different. This is more general purpose. It uses scalar threads. From Samsung, for example, HiCrest PIM are SIMD units, and they basically do multiplication and addition because they are targeting neural networks. And yeah, they are SIMD units. It's different in that sense.
Okay, many thanks again to Juan. So we will stay for the private meeting, and thanks for attending.
Thank you very much.
Thank you very much for the presentation. Thank you.
Yeah, thank you everyone for attending. I have more slides, by the way, but I think